Hello everyone. Today we are going to study about reversible logic gate. In this topic we will learn about what are reversible gate first. Reversible gate. After that we will look at what are irreversible gate. Reversible gate. We will look at some of the key criteria to say whether a gate is a irreversible gate or a reversible gate. Then we will look at the Toffoli gate. Basically, Toffoli gate is just a CC NOT gate which is designed by Thomas Toffoli uh, to make any classical irreversible gate as a reversible gate. We will look Toffoli gate applications for AND gate also. Okay. After that, fourth, we will look at how we can make any reversible means any irreversible gas as reversible gate. Make irreversible gate as reversible. So let's look further and start with reversible gate. Reversible gate. So what is a reversible logic gate? So basically reversible logic gate is a gate where for a given output we can always determine what its input was. So suppose is a gate, we don't know for now. There is a gate and through this gate we can determine that what its input were. So suppose this is our input, this is our output. So if our this is input, this is output. Okay. So if this is 0 and this is 0, if this is 1, this is 1. Okay. So this is basically identity gate. So is it a reversible gate? Definitely it is a reversible gate because if we know the output is 0, then we know that it is coming as 0 just because our input is A. Okay, so this is identity gate. Another such gate is NOT gate. So we know that this is A, this is output, and let's look. So here, if A is 0, then our output is 1, and if A is 1, then our output is 0. So through our output as 1, we can easily define that our input was 0, and through our output as 0, we can easily determine that our input was definitely 1, that's why we are getting 0. So these are interchangeable, means our output can, when we reverse our output, then we can also obtain input. So this is a way of knowing that a particular gate is a reversible gate. Now let's look at irreversible gate. irreversible gate. So we can easily understand from above that what is reversible. Now irreversible will be just opposite of that. So irreversible gate are those gate through the output only we can't determine what its input were. Okay, so one simple example is the AND gate itself. Okay, let me write it in capital AND, AND gate. So let's look at the AND gate. So we have two input and one output A, B, O. Let's write its truth table A, B, O. This will be 0, this will be 0, then our output will be 0. This is 0, 1, 0, 1, 0, 0, 1, 1, 1. So, if we look at this, our output is 1. Can we know that if our output is 1, can we determine its input? Yes, we can definitely define that since our output is 1, we can say that our input A is equal to 1 and B is equal to 1. We can determine it for this case. But what about this case? If our output is 0, so this is output, and if output is 0, so which of these three possibilities are? We don't know. It can be both A and B 0 or B as 1 or A as 1 and next as 0. So we can't define our output 0. So that's why it is a irreversible gate. So did you got one thing that there must be at least means see input is having two pin. Okay, in the previous case input was 1 and output was 1, so we are getting uh, a proper reversible gate. But here our input is 2 and output is 1. There are not enough state in output to define input, right? So can we say that there should be equal number of input and output to define at least, right? So let's see if it is possible or not first of all. So if let's look without drawing any circuit, let's just look at the truth table and see whether our theory of having equal state in input and output works for reversible or not. So suppose we are having our input, so this should be like this. So our input is A, our input is B. Means you can assume the gate like this, and this is our gate, and we are having our two input and two output C and D. Okay, So let's fill the configuration. Suppose this is the truth table. This is just an assumed truth table. So suppose this is 0, 0. Our output is coming as 0, 1. This is 0, 1. Our output is coming as 1, 0. 1, 0. Our output is coming as 1, 1. And 1, 1. Our output is coming as 0, 0. So can by looking at output we can determine our input. So let's look at any condition. So if our output is 1 1, so can we say that what was our input supposed to be? So it was definitely supposed to be 1 0. That's why we are getting 1 1. If we look at this 0 1, then we can easily say that, see, it is coming as 0 1 because our AB is 0 0. Our input is both 0. So this is. So from here we can say that if both input and output are having equal number of state, then we can consider as reversible gate. Not always. Let's see the other example. So let's have A, B, C, D. Now, what if its input output configuration were like, suppose A is 0, 0 and our output is coming as 0, 0. Got it? If this is 0, 1, our output is coming as 0, 1. If A and B are 1, 0, then again our output is coming as 0, 1. And if input is 1, 1, then 1, 0. Let's look at any of this. If 0, 0, so if it is 0, 0, can we know that what our input was supposed to be? It was supposed to be 0, 0, right? Now, if our input means our output is 1 0, so can we say that what was our input? It was equivalent to 1 1. But what about these two cases? Suppose our output is 0 1, can we define that what our input was? Because there are two input for which we are getting our output as 0 1, so we can't define, right? So looking at these two examples, you have understood that this is the reversible gate. This is irreversible gate. Irreversible gate truth table means you can understand it is, and this is the reversible gate truth table, right? So through this you can define that it is not always true if both input state and output state are equal, then only the gate is reversible. Okay, so first condition we checked, that is the important condition, that through output you can define input. This is a major condition. Second, this is sub condition type thing. So input state should be equivalent to output state. Okay, so this is the first thing, it should be satisfying. This is the second thing to determine, yeah, we need at least input state equal to output state to look for this thing? Yeah, first thing we will check is input state should be equivalent to output state. Then third thing is input and output should be distinct. Then only we can define the input, right? Here all the output were distinct, then only we can define the input. But here since two of them were same, we can't define the input. So output should be distinct, and if for MQ, yeah, for MQ, sorry, for input. So in background, dog are literally barking. So I am really getting some error. My mind is sometimes misfocusing like that. So output should be distinct, but not output. Not only output should be distinct, our input should also be distinct. For every distinct input, our output should be distinct. Means basically one to one mapping. One to one mapping is required. You know now one to one for input and output A, B, C, D. There should be all. If this should be one to one, not like A for at input. There should be like two. So it should be both way from this side and this side also. Means if it is matching from this side, then definitely it will be matching from output side also, right? So yeah, so it should be equivalent to one mapping. So since now we have understand the concept of reversible gate and irreversible gate and how to identify reversible gate, uh, so next we will move to the Toffoli gate. So what is a Toffoli gate? So basically a Toffoli gate, which is also known as CC naught gate, I will definitely let you know why it is known as CC naught or control naught gate, is invented by Thomas Toffoli. So this Toffoli gate is a universal reversible logic gate, and which means that any classical reversible circuit can be constructed from this Toffoli gate. So why we need a Toffoli gate? So there might be a condition when we have an irreversible gate, but we want its output and also want to determine what its input was. There may be a condition, so where we want its input information, but also want to leverage the output of that gate. So for that purpose, we are using Toffoli gate. So let's see what is Toffoli. So Toffoli gate is basically three-pin gate which consists of three input and three output. We know that for any gate to be reversible, there must be equal number of input and equal number of output. So this should be A, B, C. And this side it is A, means whatever we are feeding, we are getting A. This side B, and this side it can be C also, or it depends on what types of logic you required. So it will be equivalent to EB XOR C for Toffoli gate. Okay. So See, this Toffoli Gate is not a complex stuff, and yeah, many scientists have came across and whichever have created a new logic, they name those gate according to them. Okay, so if you want, there might be a Franklin Gate. What's means there? If you deduced or logic, then that gate is named on that particular fellow name. So there is nothing like what is Toffoli and means I have heard many people saying Toffoli, Franklin and other gate. So it is not a complicated thing, so don't worry about this much. So if you created if Bill Gate means if Bill Gate created some gate then it will be Bill Gate or yeah he can write Bill Gate itself. So if I created one gate so I can write as Neel Gate. So it work like that. So this is Toffoli Gate and it is generally represented by T in many reference book. So currently I am referencing Thomas Young book. So there it is mentioned as T. So you can also write in this notation for uniformity. So let's look at the truth table of the Toffoli gate. Okay, so basically before looking at the truth table of Toffoli, can we also make a circuit diagram first? So this we are making for the AND gate, right? AND gate as a reversible gate. So there should be definitely a AND gate. Let me make it like this. So there should be definitely a AND gate which will give a output as AB. We have input as AB. Okay, so we know that uh, for any gate to be having reversible, there must be having equal number of input and output. So let's pull it here and pull it here. Same information of A and B, like A, B, and this is AB. Now we can see that in the output we are having AB and AB, three three output, but in input we are still having only two. So what we can do, we can additionally add another C. But now if we add C, here output has four, right? Four pin. So what we can do, we can simply pass these two is OR gate, right? So AB is OR C. So here you can see that this is now a Toffoli gate configuration where AB and AB XOR C. So can we write a truth table for this? So you might be saying that where is now the means how we are going to obtain AB, right? Because we want to leverage the output of AND gate, but now in the output we can't see where it gone. So I will let you know how to get the AND gate output. So first of all, let's write the truth table. Now we have three input, three output. So there is a possibility that it can be a reversible gate, but not sure. So let's write the truth table for this. Truth table of Toffoli gate. So let me scroll it slightly upward. And yeah, we can start writing A, B, C. Okay, and their output has A and B, and then A, B, or C. I hope you know how to write the truth table because in the earlier video uh, sorry, I have made many videos, I think, to one entire videos on how to make truth table and yeah, so you can refer those videos also. So let's write all the possible A, B. Suppose you can assume it like this. Our initial output for our AND gate. Okay, this will be 0, 0, 0, 1, 1, 0 and 1, 1 because this is our main input. This is our main input and C we additionally added. Okay, for our reference purpose. So this is 0, 0. So C can be either 0 or 1. Yeah. So first case 0. Then again if AB is 0, 0, C can be 1. So there will be for each input there will be two corresponding input along with C. So we can write all other combination 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I know my writing is bad, but yeah, you can try to bear it because I am writing it digitally. So now we know that A and B there is nothing changed because we are directly pulling the thread A, B, B. There is no operation performed. So A and B will be same. Yeah. So this will be 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1. Wait a second. Um, Let me write it in order itself. Yeah, 0, 1, 0, 1, 0, 1, 1, 1, 1. Yeah. Should I draw a line also as a separator? Yeah. Yep. Now, what will be our AB XOR C? You know AB XOR C, how to get AB XOR C, right? So, I am just writing the table 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, and then this will be 1 and this will be 1 and this will be 0. Okay, so these are input and these are output. So from here, if we look at this, yeah, here only we can look. So AB is input, we are having one output. We know that for 0, 0 it is 0, 0, 1 it is 0, 1, 0 it is 0, and for 1, 1 it is 1. So let's try to pull this configuration with some uniformity. So if you look at this input output pattern, you will see one thing, definitely one thing, if you are focusing properly. So we are having C as 0 or 1. So if we look at C0 only, okay, C0 only. So can you see one thing? If AB is 0, we are getting 0. If 0, 1, then we are getting 0. Yeah, again 1, 0, we are getting 0. And if 1, 1, then we are getting, here it is 0, 1, 1, then we are getting 1. So wherever C is equivalent to 0, so there we will get our AND output. Okay, can we check what if C is equal to 1? Let's see. Now let's check for this configuration. Will it work or not? So 0, 0, no, we are getting 1. So it is not correct, right? Again 0, 1, again we are getting 1. So it is not correct. 1, 0, again means 1, 0, again we are getting as 1. So it is not correct. 1, 1, we are getting as 0. It is definitely not correct. So from here we can understand that wherever C is equivalent to 0, our C input is 0, then we are getting our output of A, B, our output of AND gate. So do you see a weird pattern? A little is one pattern where by which this is known as CC not gate, control not gate. So I was means in the earlier just before when I was defining the Toffoli gate, so there I have mentioned why means there I have just mentioned the CC not means CC not reference. So why it is called as CC not? Why it is called as control not gate? So if you look at the last two configuration, okay, here if you see when A and B both are 1, right, our output is getting changed, our C is getting changed. So here what C was 0, now it is flipping, our third bit is flipping to 1. Now if this is 1 and this is 1, our this bit is getting flipped, right? So see, you can write it like, means should I write it separately or you are understanding it here only? That is one thing which is creating mess. So if this is our A, this is our B, this is our C. When our A is 1, B is 1 and C is 0, what our output we are getting? A, B and our AB or C. So this is the same ABC. Now both of them are 1, then C is flipping. We are doing the not of C. So basically C is flipping. Since C is 0, now it is becoming 1. So if C is 1, then it is becoming 0. So what is happening is controlled. When we are giving control to A and control to B, then our not operation is performing. That is why we are saying control, control not. if you go above and if you see, then it is not happening with other bit. Here we don't have control to A, B, so our C is same. Here also it is 1, means it is not flipping. So same for 0, 1, we are having control in B but not control in A, so our C is not flipping. So like that. So you can draw, means in while you will use IBM, you will also draw the control knot like this. So this is our input A, B, C. So how we draw control knot? So this is A, this is B, and here we are flipping the bit. So we draw it like this. So when A is active and B is active, then only this NOT gate will be activated. Else this NOT gate will not be activated. So that's why Toffoli gate is also called as CC NOT gate. Okay, so you can try to make other gate as a reversible gate also, but we will definitely make, means in the next video anyhow, we are going to study about how to make a irreversible gate as a reversible gate. Since this video has become long, I will make that video as a separate video, so that there we can practice some more questions on how to make a irreversible gate as a reversible gate. So I hope you have get some information from this video, and if you are new, so I make videos on current, means I am working on making videos on quantum computing. But before quantum computing, I want to just have some basic understanding of the classical computation and how we are encoding, how we are, means what all gates are. So this CC NOT gate will be utilized while we are working on the quantum also, because there are several conditions where we will be applying the control NOT gate. So so that's why I am covering this classical computation. After the finish of this classical computation, only few topics more are remaining, like how to make a reversible gate. Then there is some topic on error correction, and then we can move to our classical, means our quantum computation, where basic understanding will be given. So I hope you like the video. So see you in the next video, where we will be discussing about how to make a reversible gate, means I'm continuously saying reversible, how to make a irreversible gate as a reversible gate. So thank you.